In this video, we will talk about significant figures and how to do calculations to reflect the correct number of significant figures. Significant figures are a simple and effective way to represent the precision of a measurement or a number that reflects a calculation from a measurement. And so within a number or a written string of digits that represents a number, some of the digits are significant and some of them are not. And so we have some rules that describe what is what. Okay, so all non-zero digits, this is rule 1, all non-zero digits and zeros between non-zero digits are significant. So this basically means if it's a number that's not zero, it counts, it means something. So say we have 735. This number has 3 significant figures in it, and I'm going to underline them to say all 3 of these are significant. These are numbers, they mean something. Okay, now if you have 4,305.02, your overall string is 6 digits long, and in this case all of them are significant because the zeros here are in between other numbers, which makes them significant. It is just actually 0, no need to discriminate against it because of that. Okay, now rule number 2, zeros to the left of the first non-zero digit are not significant. So this is really where the trouble begins when we start figuring out how to deal with zeros. So zeros on the left, not significant. In this case, the 2 zeros on the left are just there to denote place value, that 305 is actually a fairly small number. It's 0.0305. And those zeros are not part of the measurement itself. They're just there to determine place value. Whereas the 305 at the end, the ones that are now underlined in green, those digits are significant. Another example, say you were to write 0301. This one's kind of silly because nobody writes numbers that way. But if you were, the first 0 on the left is not significant, the 3 on the right are. One more example, if you have 0.0002, only the 2 is significant in this case. And here it'd probably be more effective to write it as 2 times 10 to the negative 4th. And this shows the one significant figure in the represented by the number 2. Okay, so then rule number 3, zeros to the right are significant if they're also to the right of the decimal point. So say you have 25.0. This 0 is significant. It counts, it means something. The fact that you took the extra effort to write the 0 means that it actually represents 25.0. It tells you about your precision. Do you know this? Oh, it's about 25, or do you know this? It is exactly, or I shouldn't say exact, but this is very much 25.0. This is a case where your calculator will lie to you. If you type in 25.0 to your calculator and press enter, it chops off that extra 0 because it doesn't think you need it. And mathematically, no, you don't need it. But chemically and measurement-wise, when you're talking about that 0, it's really important. So this number has 3 sig figs. If you say 19.050, okay, the 1, 9, and 5 are significant due to rule number 1. The 0 that's trapped in between the 9 and the 5 is significant because it's between 2 non-zero numbers. And then the 0 at the end is also significant because it is to the right of the decimal point. Okay, so now rule number 4. Zeros to the right when there's not a decimal point are ambiguous, is basically what this says. Because you don't know if it's, in the example here, 2700, you don't know if it's actually 2700 or if you're just rounding to make it sound like more of a round number. So it's kind of ambiguous. This is where the decimal place matters. If a 0 is to the right and there's a decimal place, it's significant. If the 0 is to the right but there's no decimal place, it's not significant. So in the case of 2700, it's ambiguous. The first 2 you know are significant, the other 2 you don't know. So let's write this a couple different ways. So say you were to rewrite this 2.700 times 10 to the 3, okay, then you know that all 4 of those digits are significant. Or if you were to write 2.7 times 10 to the 3, okay, the zeros are not significant, you had some number that you just rounded, okay. A good example here is saying that St. Mary's has 2,700 undergraduate students. Well, you didn't measure how many students there really were, you're kind of ballparking a rough number, right? So you don't know if those zeros are significant or not. People do this a lot in common discussions. It's a much easier thing to say than 2,752, right? Another thing you can do that's kind of a shortcut is you can write 2700 with a decimal point on the right side. And this is the same thing as saying 2.700 times 10 to the 3. You're saying that all the digits to the left of the decimal point are significant. In this case, all 4 of them are significant. It's kind of a shortcut to do it this way. It's preferable to use scientific notation when you can, but sometimes it's just easier to throw the decimal point at the end. Okay, rule number 5. Numbers that can be counted exactly are exact numbers, and thus they don't really play into the sig fig discussion at all. So if you say 5 eggs, assuming they're whole in the shell, you can't really have half an egg. If you cook it and then chop it up, that's another story, but an egg is an integer number. Your recipe calls for 3 eggs, 5 eggs, right? And so that's an exact number. It's not really 5.01 and you rounded it to 5. It's that this number is 5. The same is true if, say, you had 75 cats. You can't really have half a cat, so you know that this is a discrete integer number, 75. We call that an exact number and say that it has, I say it doesn't play a role in determining sig figs. You can think of it as having infinite sig figs. And if you had 75 cats, well, that's a lot of cat food. Do note that there's a worksheet posted on Moodle that I also handed out in class that has these rules and some further examples listed on them. Okay, so some examples. How many significant figures are present in the following numbers? So I will encourage you to pause the video and then take the time to work this out and test your knowledge of the subject, and then resume the video and we'll talk about the answers. Okay, so the number 24.2 has 3 sig figs in it because all of these numbers are non-zero, so by rule number 1 there's 3 sig figs. If you go to 204.2, well, that 0 is sandwiched in between 2 non-zero numbers. That makes it significant, a total of 4 significant figures. Whereas if you say 0.0242, the 2 zeros on the left are not significant because they're just there to determine place value, and they don't count in the measurement. So you have 3 sig figs in this number. One handy tip is if you were to put 0.0242 into scientific notation, the zeros on the left go away, which means that they must not be significant. Okay, the next one here, 24.20, since you wrote the 0 to the right of the decimal point, it means it's significant. Whereas if there's no decimal point there, you have 2420. This is ambiguous. It's either 3 or 4 sig figs. You should write this in scientific notation to make that clear. Okay, and then if you have 5 people, that's an exact number. We don't think of that as having a certain number of significant figures. When you're doing a calculation with an exact number, it doesn't affect the sig figs of the other numbers. Okay, so now that we've talked a little bit about what sig figs are, we should mention why we care about them and where they come from. So ultimately, significant figures are determined by an experimental measurement in the lab, and some of these measurements have more or less precision, which lead to more or less significant figures. So for example, the top left here is a picture of a volumetric pipette, and if you look closely at it, it says that the volume is plus or minus 0.02 milliliters, which tells you that you should write the volume that you dispense out of this pipette as 10.00 milliliters. Because if the error is only 0.02, well, your error is contained in the hundredths place. So you need to write 10.00. On the right, we have a picture of 2 pirettes, where it's an analog scale, so it's tick marks on a scale, and probably a little hard to see, but if you can pause it and zoom in somehow if you'd like. The one on the left, the initial reading is a little lower than 9.6. One thing to note here is that the scale is upside down, so smaller numbers are at the top and bigger numbers are at the bottom. So when you're past 9.5, it means you're 9.6, but it's a little past 9.6. you can estimate, all right, it's maybe 0.2, 0.3, maybe even 0.4 past the 9.6. Although to be fair, I should have said 0.02, 0.03, and 0.04 milliliters past the 9.6. And that tells you something. That's good enough to write down. So when you're looking at an analog scale, you always estimate one decimal place beyond what the scale gives you. So the scale on the burette gives you tenths, 9.6, 9.7, and then you estimate where you are between the tenths. And you write into the hundredths place. So the final reading on the right, say you have 24.16. And there'll be a little bit of error in here. You could say 24.15, depends on how you look at it. But overall, that's more precise than just saying 24.1 or 24.2. And you get a little something extra out of it. Now, when you're reading off a digital device in the lab, you just take all the numbers that are on the scale and call those all significant. Never remove numbers from your measurement. Don't look at this 126.8713 and say, 126.87, whatever. If you're going to write down the number, write down all the numbers. Now that we know how to identify significant figures in a number, we need to talk about how to do calculations with numbers with certain amounts of significant figures. And this is a real-world scenario in that you measure something in the lab with a certain amount of precision, and then inevitably you have to do some calculation steps, some math to figure out what the quantity you care about actually is, which is usually something mathematically related to your experimental numbers. And in doing so, you need to keep track of the correct amount of significant figures. Okay, so how you deal with the significant figures in a calculation is grouped by whether you're multiplying and dividing or whether you're adding and subtracting. And in this case, squaring something or taking an exponent counts as multiplying and dividing because really you're just multiplying something by itself. So say you have this equation, 2.37 times 24 gives you 56.88. So I call 56.88 the calculator answer. It's what your calculator gives you. Your calculator may have given you even more digits beyond that. Who knows? Again, your calculator lies. It tells you, here's all the digits, but not all of them are significant. So in this case, 2.37 and 24, all right, 2.37 has 3 sig figs, 24 only has 2 sig figs. So looking at the rule, the number of sig figs in the answer is the same as the number with the smallest total amount of sig figs. So in my head I say, this depends on total number of sig figs. You have 24 on the left, that only has 2 sig figs, therefore your answer only has 2 significant figures as well, 56.88. So then you rewrite this to say the answer is 57. You round it to the significant figures, in this case only 2, using your normal rounding rules. Another example, 2,908 divided by 3.1. Your calculator tells you 938.06 something. And you look at this, the 3.1 only has 2 sig figs, so therefore your answer only has 2 sig figs. So first step, you might write 940, but remember that a 0 to the right of a number without a decimal point is ambiguous. You don't know what that means, so don't do that. Instead, write 9.4 times 10 to the 2, which shows very clearly that you have 2 sig figs. All right, yet another example, if you have 2.7 cubed, you get 19.68 something. 2.7 has 2 sig figs, 19 has 2 sig figs, so you can round to 20. In this case, you can get away with putting the decimal point on the right side to denote that both the 2 and the 0 are significant. When you're adding or subtracting, it's a different rule. In this case, place value matters. The number of digits to the right of the decimal in the answer is the same as the number with the least number of significant decimal places. That's kind of a mouthful. Let me show you instead. So say you're taking 9.0 plus 1.907. I'm going to rewrite this, and okay, I calculated the answer. Now your answer has the same number of decimal places as your original number with the least number of decimal places. So in this case, 9.0, we're only significant to the tenths place, the first decimal place. And even though 1.907 is significant beyond that, we're limited by the fact that the top number only goes to the 10th place. So therefore our answer only goes to the 10th place. So then we say we have 3 sig figs in our answer, and this equals 10.9. So notice that we started with a number with 2 significant figures, and we ended with a number with 3 significant figures, because it's not the total number of sig figs that matter, it's the place value. It's the fact that it's 0.0 and 0.9. There's only one decimal place there. Okay, right? So the rules are very different for adding and subtracting versus multiplying and dividing, and it's really easy to get them mixed up. There is some logic here as to why it works. Try your best to remember it. Okay, some other things to note is that integers and exact relationships don't affect sig figs. If you had, say, 190.35 pounds times 5 people, then your answer will still have as many sig figs as your original number, and it will not just have 1 sig fig because of the number 5, for example. So the 5 doesn't, the number of integer people doesn't affect your sig figs of your other number, because you're multiplying by exactly 5. There's no experimental precision there. Another thing that's very important is if you have a multi-step calculation, is to carry around the extra significant figures until the end and then round at the end. Sometimes you can get yourself into trouble if you round early, because then you'll have a slight error in your number because you rounded when you weren't supposed to. And we have some examples of that on the next slide. This is really important for the homework because I really want Moodle to keep you honest about sig figs, but I don't have a good mechanism to do that other than to be very nitpicky, and it nitpicks by making sure that you keep all the digits around and then round at the end of your big long calculation. So do keep that in mind. I suggest 2 extra digits to just carry these around through your calculation, and then in your intermediate steps you can underline the numbers that are significant so you can keep track of them, but then ultimately round at the end. Okay, so here's some more practice. Please pause the video and try to work out these problems on your own, and then resume to hear me talk about the answers. Okay, so on the first one we're adding, and the calculator answer looks a little something like this, 20.4215. But since there's only 2 decimal places in the 20.10 number, then your answer only has 2 decimal places. Whereas if you multiply these numbers together, well, it's a different rule when you multiply and divide. Here we are worried about the total number of significant figures, which is 4 for both numbers. They both have 4 sig figs. And so then you round your answer to 4 sig figs total, irrespective of where the decimal point is. Alright, if you were to take 23 divided by 5.217, well, you don't know that the 23 is exact. It might be some measurement that's rounded to the ones place. You don't know. So unless you're told explicitly that something is an exact quantity, treat it like it is an experimental number that has only the precision you see. So in this case, 23 has 2 sig figs. Since you're dividing, you go with the total number of sig figs, and then your answer comes out to be 4.4. Alright, so the multi-step calculations on the bottom, follow the order of operations first, so do what's in the parentheses. In this case, 4.4 plus 12 adds to 16.4. Now, within the parentheses, the 12 doesn't have any decimal places that are significant, and so your ultimate outcome of the addition operation does not have any significant decimal places. So I underlined the 16, I left the 0.4 so I wouldn't get rounding errors. And then you divide by 5.301. Now your 16.4 number has 2 sig figs. 5.301 has more than that, so your answer has 2 sig figs, and then you round it to 3.1. Another thing to point out is what would happen if you rounded in your intermediate step instead of rounding at the end. So if you were to take the intermediate step and round it to 16 divided by 5.301, your calculator would tell you the answer is 3.018, which since 16 only has 2 sig figs, you'd get 3.0. This still has the right number of sig figs, still 2 sig figs in the answer, but the number's different. So sometimes you get these small little errors that can creep in if you round after intermediate steps. In the real world, they're not such a big deal, but the Moodle homework does tend to really care about that kind of thing. So just get in the habit of rounding at the end of your calculation and keeping track of what numbers are significant by where you underline. Okay, so this concludes our discussion on sig figs, but one thing to say before you go is please take the time to learn sig figs really well right now. In almost every problem throughout the year of general chemistry lecture and lab, any problem where you're calculating a number, you're expected to provide the right amount of significant figures for that number. If you don't do that, then you're going to lose some points on that problem. And it's really frustrating to understand the concepts of this whole assignment or exam or whatever, but then lose 5 or 10% to improper sig figs. Okay, hopefully with that pep talk you're ready to learn sig figs, and definitely practice this and keep on it, and you'll get better in no time.